Welcome to our final project, Navigating the Sea. And what this is going to talk about is we're going to talk a little more about how sailors would navigate the ocean back then without the navigation systems that are built today. Well, I just want to go over a few course ideas that were used and that we felt tied into the topic that we chose. And a few of those are angle of elevation, our right triangle trigonometry, dealing with sine, cosine, tangent. Not only that, but I feel application of trig to real world measurements really is something that they practice a lot. I mean, a lot of their measurements were done real world. The big question that we really want to answer is, how did ancient sailors use angles and trigonometry to navigate the oceans? And I hope by the end of the presentation, everyone should be able to answer this. So first off, I want to talk about why navigation was important. Well, knowing how to navigate was essential for sailors because the ocean had no landmarks. It wasn't like they had mountain ranges all over the open sea to help them know where they were, or specific things that would stay in one place over time. The ocean is constantly changing, so they had to use the stars. But the successful navigations helped with exploring, trading over continents, and just overall a more successful navigation. The development of navigation tools and angle measuring techniques really helped them in the long run. In this next slide, where we talk about our key navigation tools. And a few of these are like our magnetic compass. We have a right arrow that always points north, so we always know where north is. And what this did is it really helped improve accuracy in navigation and map making, allowed sailors to stay on course during long voyages. They also used the astrolabe, cross staff, sextant, and those are just a few of them, but we're really going to be focusing on the sextant. And what they did is it allowed for more accurate navigations, it made long distance travel safer, and it reduced guesswork. And it all had the same purpose of helping in long distance travel. Now for this next slide, we have a few pictures and it kind of shows us a bit more in depth on what we're talking about with the compass. We see this red arrow, and normally that would always be facing north, and this would be where you are relative. And then over here we can see we have a sextant, and we can see here we have our bridges, and then we have our angle measurements that they would use when using these mirrors to reflect the stars from the sky. And then here we have what maps would have looked like using the compass or sextant. From here, I think I will hand it off to our next presenter, Amanda.
Thank you, Isaiah. I'll go ahead and cover just a brief overview of what the ancient trade routes and specifically what the Silk Road was. It wasn't just a land route, but it included major sea routes. This bolstered development of this technology and allowed us to not only find better ways of travel, but making it more dependable. Furthermore, we'll move onward. So we'll go ahead and figure out why it was so important for what sextants are, what they measured. Some key features of sextants included their ability to measure the horizons in addition to the celestial object. So it would go ahead and measure either the sun, the moon, a star, and then compare that to our horizon. Lastly, after identifying the accurate angle in addition to the time, they would go ahead and compare that to the nautical almanac. This would help them identify the longitude and sometimes the longitude. We'll move on to the history of sextants. In the 18th century, British mathematicians created this technology to go ahead and create better measurements of the celestial angle. Sextants were made to make ocean travel more dependable, and this became essential for global travel and global trade. Lastly, I'll go ahead and cover why this angle was so important. Prior to sextants, traders used dead reckoning. This measurement was inaccurate just because sailors would use direction and their distance traveled. This made absolutely no sense, as each trailer would begin at a different position and travel to many different positions, having absolutely zero angle. Thus, the Polaris angle is so unique as it's almost directly above the North Pole, allowing any sailor in the northern hemisphere to have an exact latitude. I'll go ahead and pass off our remaining slides to our next speaker.
Hello, my name is DenaIliana, and I'll be talking about how trigonometry is behind the sextant. The principle behind the sextant comes directly from right triangle trigonometry. When a sailor measures the angle between a star and the horizon, they are actually creating a right triangle, the horizon being that base, and the angle at the sailor's eye is the angle of elevation. The relationship between the sides and angles, which we call them sine, cosine, tangent, and their inverse are the same relationship sailors used. As navigation improved, more mathematical corrections were added, but the basic idea stayed the same. This showed how trigonometry became a powerful tool for real-world problem solving. Now we did create some distance examples. Let's say a sailor sees a lighthouse that is 60 meters tall. The lighthouse appears at an angle of only 0.5 degrees above the horizon. Using the tangent function, distance equals 60 divided by tangent 0.5 degrees. This gives us a distance of about 6,870 meters, or roughly 6.9 kilometers away. We did also create an inverse trigonometry example. So when working backwards from an angle to find a location, sailors are using inverse trigonometry functions, the same ones that we use in class. By measuring how high Polaris appears in the sky, sailors formed a right triangle and then used the inverse tangent idea to determine their latitude. For example, if the sextant measured Polaris at 41 degrees above the horizon, the sailor's latitude is approximately 41 north degrees. This method made navigation far more precise and allowed sailors to explore the world with mathematical confidence. Thank you for watching our presentation. If you have any questions, comments, or want more information, feel free to contact me on the email shown on the screen, so you can contact my peers on their emails. We appreciate your time, and we hope you enjoyed learning.